Dear students, after studying this module, you shall be able to know what is meant by pyrolytic elimination. You will be also learning about the type of substrates which undergo pyrolytic elimination, and you will be able to know the mechanism and the stereochemical aspects of the pyrolytic elimination. And you will be also able to distinguish between the various types of pyrolytic elimination and analyze the pyrolytic elimination, especially of the acyclic and alicyclic systems. Let us first understand what is meant by the term pyrolytic elimination. It literally means an elimination reaction occurring in the organic substrate due to the application of heat, because pyrolytic means heat. In organic chemistry, pyrolytic elimination do occur thermally and do not require any additional reagent or solvent to occur, and mostly are carried out in the gaseous phase, though they can also be performed in inert solvents presents. These thermal elimination reactions of molecules can also be termed as pyrolytic EI reactions, which stands for elimination internal reaction. Note that EI is not intramolecular elimination, it is the internal elimination reaction. Now, for example, let us consider the case of ethyl acrylate. If you heat the ethyl acrylate, and this will be leading to the formation of acrylic acid and ethylene, as you can see in the reaction here. Now, let us progress ahead and look at more details of the pyrolytic elimination. We will know about the various pyrolytic eliminations based on the position of the leaving group, and accordingly these may be classified as alpha elimination, beta elimination, or 1,3, 1,4 and so on, or you can say it is 1N elimination. And though out of all these, the beta pyrolytic elimination are the most common. If we talk about them one by one, coming first to the alpha elimination involves the elimination of the two leaving groups which are connected to the same carbon atom, and these type of elimination are most commonly encountered where the more common beta eliminations are not possible. For example, if you consider this case where the Cl and H are being eliminated from the same carbon, and as a result you are getting a 3-member cyclic ring. Similarly, there is another elimination that you are already familiar, which happens in between as intermediate formation. There again, from chloroform, the removal of H and Cl, and it gives you the dichlorocarbene. So that is also the case of alpha elimination. And now coming to the beta elimination. Beta elimination occurs when two groups are lost from the adjacent carbon atoms, and as mentioned, they constitute most of the pyrolytic eliminations with a typical even mechanism, and this is the most common, the very first elimination that you have studied, that is if you have the dehydrohalogenations from the alkyl halides giving you the formation of alkene, or the dehydration of alcohols giving you again the alkene. So all these eliminations which you have normally studied till now, they are in beta elimination, the two groups which are lost are from the adjacent carbon atoms, and in contrast in alpha elimination, the two groups which are being lost are from the same carbon. Now, after knowing the alpha and beta eliminations, let us see what are 1,3 and 1N pyrolytic eliminations. Now, when we talk about the 1,3 elimination, obviously it means that the two groups which are being lost are from the relative first and third carbon atom, and as you can see the case of 1,3 pyrolytic elimination here, the OCOCH3 group and the H are being lost from the relative 1,3 position, and as a result you can see here we are getting a new 3-member cyclic ring getting formed, and the CH3COO and the H are being lost as acetic acid. So this is the case where 1,3 elimination is happening, and similarly you can have the 1,4 elimination, the 1,5 and so on, and so they in general are called as 1N pyrolytic elimination. Now, after becoming familiar with the different types of pyrolytic elimination, how they happen, we will now look into the mechanism of pyrolytic EI elimination. The pyrolytic elimination occur most commonly via the EI mechanism involving a cyclic transition state which may be comprised of 4, 5 or 6 member transition states. Note that it is a concerted mechanism and is almost exclusively a syn elimination, and there are various evidences of this mechanism, and this can be noted like the first thing is the evidence of this mechanism are that it is a first order reaction kinetics. The other important parameter is that no reaction intermediate has been isolated, so it is a concerted mechanism, it is a single step simultaneous mechanism happening. Then another evidence and the parameter you can look is the free radical inhibitors. When they are added, they show no effect on the reaction. Another thing to notice is they show a negative entropy of activation, and furthermore is the exclusive syn elimination which is demonstrated experimentally. We can have a better understanding of the mechanism by taking an example. The pyrolysis of the erythro and trio isomers of 1-acetoxy, 2-deutero, 1,2-diphenylethene gives in each case the trans stilbene, but the stilbene from the erythro compound retained all the deuterium while the trio compound lost all of it. Now, this must be due to the syn elimination of hydrogen or deuterium atom and the acetoxy group. So, these two, that is the hydrogen and acetoxy group, are being lost in one case, in another it is the deuterium and the acetoxy group. And the preferred conformations for syn eliminations are those in which the phenyl groups are as far removed as possible from each other, which explains the experimental results. So, if we look at both of these cases, what we find is clearly it is showing that this mechanism proceeds via the syn elimination. Let us now see the different aspects of pyrolytic elimination in acyclic and alicyclic systems. If two or more syn periplanar arrangements are available, the one with least crowding is preferred. Pyrolysis of 2-butyl acetate, as you can see here, affords a mixture of 1-butene, cis-2-butene and trans-2-butene with the trans to cis ratio around 2. And this is because there is less steric hindrance or less steric interaction between the two methyl groups in the transition state, leading to more of the trans alkene. So, you can clearly see in this particular example that this elimination is giving you both the double bond coming at the first position or at the second position, but when it comes at the second position, out of cis and trans, it is the trans which is the major product. Now, continuing with the aspects of pyrolytic EI elimination in the alicyclic systems, the additional restrictions are imposed by the conformations of the leaving group and the obligation to form the cyclic intermediate. As we have told that the cyclic transition state is formed. So, obviously, if you look at the conformation of the cyclic ring, what you find is this OCO SCH3 group and the H, they will be lost via cyclic intermediate, and for doing so it has to be the syn elimination. So, you cannot have that the H is on the other side of the plane of the ring and the other group is on the other side, and that is being clearly reflected in this particular reaction. So, you can see in this given example that the double bond can be formed relative to methyl at the first position or at the second position. So, it is almost 50% mixture of the two, that is you are getting 1-methyl cyclohexene and you are getting the 3-methyl cyclohexene as the corresponding products. Now continuing this discussion further, this point is made clearer by the example of ethyl 2-acetoxy cyclohexane carboxylate, as you can see here, in which the leaving group is axial. The double bond in the direction of carboxyl group does not form even though it would be conjugated, since there is no equatorial hydrogen on that side. However, in the case of its diastereomer, in which the leaving group is equatorial and the hydrogen is the carboxyl group is axial, can adapt the necessary cyclic transition state that leads to the conjugated alkene. So, you can clearly see here again it is going via the syn elimination wherever there is the cyclic transition state is being favored. Furthermore, when the leaving group is axial, it cannot attain a cyclic transition state with a neighboring axial hydrogen. So, when the leaving group is equatorial, on the other hand, it can form the cyclic transition state with either an equatorial which is in trans relationship or axial which is in cis relationship with the hydrogen atom at adjacent carbon, as you can see in the example of methyl cyclohexyl xanthate. You can clearly see here the OCS-SCH3, the group which is being lost can be lost with this equatorial hydrogen or the other axial hydrogen. But out of these, the cyclic transition state will be favored when the this group is in equatorial position. Let us now know the free radical pyrolytic elimination mechanism. Free radical elimination is found in polyhalides and primary monohalides. The steps are very similar to any free radical reaction, that is, there will be a chain initiation step followed by several propagation steps, and then finally there will be termination steps. Let us now understand the free radical pyrolytic elimination mechanism. This free radical elimination is found in polyhalides and primary monohalides, and here the steps are very similar to the free radical reaction that you are already familiar, that is, there is a chain initiation step, and here there will be formation of free radicals, like for example if you take R2CH CH2X, and this on heating will give rise to R2CH CH2 dot and X dot. So you can see here this cleavage is happening, and this is the homolytic cleavage, and we are generating the free radicals. And in the chain propagation, this free radical will be attacking or more neutral molecules. So this is the free radical that we had formed in the initiation step. You can see it will be abstracting this hydrogen, and as a result there will be formation of this radical. And similarly there will be other possibilities also. And in the chain termination step, eventually all the free radicals will be combining to give the neutral products. So this can happen this way, or even the C dot can be attacked by X dot. In that case there will be formation of this product, and so on. So you can see that this is the way where the pyrolytic elimination is happening via the free radical mechanism. And the main result of the free radical pyrolytic elimination we can sum up as that R2CH CH2X, when pyrolyzed, that is heated, then we get, so you can see here that there is a removal of H and X, and as a result there is a double bond which is getting created at this position. In this free radical mechanism, sometimes there may be a scission process resulting in the formation of alkene and another radical. Like if we start with this butyl radical, then it can undergo formation of this another radical and formation of this alkene. So you can notice here that it is going into cleavage here, and this part is giving this alkene, and on the other hand this is what is the free radical which is being formed. The free radical elimination can be followed by rearrangements, such as you can consider this particular case which is being shown here, which is 9,9 dimethyl fluorine, and you can clearly see in this particular example is that there is first removal of the CH3 radical, so that you get the radical at this particular position, and out of this there can be removal of the hydrogen free radical to give you a exocyclic double bond, or there can be rearrangement and then the removal of the hydrogen radical happens, and as a result you get this aromatic phenanthrene system. Now, after studying the various pyrolytic elimination, let us try to know some synthetic importance of these reactions. Pyrolytic elimination occur in a variety of substrate containing appropriate leaving groups and are important from a synthetic perspective. Considering the pyrolysis of esters, the pyrolysis of esters is usually effected at high temperatures. Usually it is 300 to 500 degrees centigrade, which are a serious limitation to their synthetic usefulness. Now, since these reactions do not necessarily require any solvent or base, hence these reactions are clean to perform, the isolation of product is very simple. The high temperature required for pyrolysis of the carboxylic esters has limited synthetic usefulness. So, you can look at these two examples shown here. If you look at the ester pyrolysis, on heating this particular ester around 300 degrees, you are getting ethene and carboxylic acid. In general, this is the general reaction, and if you consider this particular example where this cyclohexene is joined to these two ester groups on heating around 500 degrees centigrade, there is a elimination of OCO, CH3 and H, and as a result you are getting these two double bonds which are exocyclic to the double bonds. So, this is again, you can see this is highly directional here, and otherwise preparing the exocyclic double bonds is difficult. So, you can prepare these type of molecules through this particular reaction. After studying about in general the pyrolytic elimination, now let us consider some named reactions, and first of all let us consider the Chugaev elimination of xanthates and thianocarbonates. The Russian chemist, that is Alexandrovich Chugaev, discovered a way to eliminate water from alcohols to produce alkenes via the formation of an intermediate xanthate, and this methodology came to be known as Chugaev reaction. Examples of this, if we consider, let us consider them one by one. The Chugaev reaction has been, if you look at the examples, what we find is, you consider the case of this particular alcohol, which when reacted with CH2 in the presence of NaOH and CH3I, what you get is, you get this OSS, this is the xanthate derivative which you are getting, and then on heating this xanthate group and hydrogen eliminates, and as a result you are getting alkene. Note that if you have to directly eliminate the alcohol into alkene, that will require acidic medium and it may go into rearrangement, so it will not be happening at that very particular position. So, in this Chugaev elimination, we are converting the alcohol into the intermediate xanthate, and this xanthate can be easily further undergoing into pyrolytic elimination, that is elimination with heat, and you get the corresponding double bond at the required position. Coming to the other example, what you can see here, this again having this OH group, and this OH group can be removed and the adjacent hydrogen can be removed via the genthate. So, here also in the first step we do the reaction with sodium hydrides, the CS2 and ethyl iodide in the presence of THF, and we heat, we will be getting the genthate, and then second step will be heating it around 160 degrees centigrade. So, there the pyrolytic elimination happen, and as a result you can notice that this double bond is getting formed. So, there is overall elimination of water from this alcohol, which is a substituted one, but note that the COH is not getting affected. So, the only overall reaction is the removal of this H and OH, and as a result we have this alkene which is getting formed. Furthermore, note that the Chugaev reaction, it has been successfully employed for beta elimination of alcohols to yield alkenes due to the milder reaction conditions involved than that used for ester pyrolysis. Thus, if a carboxylic acid or ester and an alcohol functionality is present on the same molecule, the alcohol can be chemo and regio-selectively eliminated to give an alkene, as we have seen in this particular example. And this is very successfully employed and useful in the synthesis of natural products. Now, after the Chugaev reaction, let us consider another named reaction, which is Cope elimination, and we can call it as the Cope elimination of tertiary amine oxide. The Cope elimination developed by Arthur C. Cope is an elimination reaction of the N oxide of a tertiary amine to form an alkene and a hydroxylamine at milder reaction temperature, and these milder reaction temperature, they are in the range of only 100 to 200 degrees centigrade. The mild condition of the Cope elimination, as you can see in the example, in the synthesis of 1,4-pentadiene, permits the generation of a new alkene bond without eventual rearrangement into conjugation with other unsaturated systems. So, this is very important thing to note, because unlike the eliminations which you have studied earlier, where there is rearrangement which is very common, and if you wish to prepare the molecule having two double bonds, that is a diene at these positions, then it is difficult, because most often you get a conjugated diene which is more stable, because when you have the Chugaev elimination route, like in acid catalyzed dehydration of alcohols or the dehydrohalogenation of alkyl halides, they will be giving you only a conjugated diene as the major product. So, in contrast, coming to Cope elimination back here, the elimination is giving you a very regio-selective elimination where you are getting the double bond at this terminal position. The Cope elimination is also a syn elimination if we talk about the stereochemistry, and it involves a 5-member cyclic transition state which must be planar, and it is syn coplanarity which is there. So, again the two leaving groups, they have to be stereochemical wise, they have to be on the same side, then only the transition state formation is there. The amine oxide, which is the leaving group, which itself acts as a base here, and the net reaction is the 1,2 elimination. So, you can see they are the two groups which are getting lost, the H and the N oxide, they are relatively from the 1,2 position. This syn periplanar leaving group and the beta hydrogen positioning, that is a 1,2 positioning of the leaving groups, can be clearly seen from this particular example, where this hydrogen and the N oxide group, they are undergoing a transition state formation. They require their syn periplanar positioning, and these two groups you can see are getting lost from the same side, and that is why you are getting the corresponding geometry of the alkene where the two methyls are on the same side, and the hydroxyl, the substituted hydroxylamine is the byproduct. The sterically demanding amine oxide reacts preferentially with the more easily accessible hydrogens and often gives good selectivity favoring the less substituted alkene. Thus, Cope elimination is regioselective, and for simple alkenes, the reaction follows the Hofmann rule, which is opposite to that of the Sage's rule. So, as you can clearly see in this particular case, the NMe2, this particular quaternary amine, this will be via the amine oxide, the double bond it gets in this particular second position, where the 71% is there as the product of the trans geometry and it is only 29% product which is or the cis geometry. And if you look at the in between the amine oxide intermediates, you can clearly see why this is 71% and why the other one is only 29%, because when you have this H and amine oxide on the same side, then it is the syn periplenarity which is possible. So, this will be preferred versus the other where the hydrogen and this bulky group are on the same side. So, this particular, although the H and amine oxide are on synplanar, but this conformation will be less stable because of the bulky groups coming very near. So, out of these two, the one which is preferred will be having the less steric hindrance in the conformation, and that will be telling you which should be the major product. Let us consider another example for even more better understanding of Cope elimination. As we already now know, Cope elimination is regioselective, and how we can get satisfied with this? These structures, you can see, they will exemplify the stereochemical requirement for reaching a 5-member cyclic transition state and the influence of sterically demanding groups for some cyclic compounds. Thus, heating the dimethyl methylamine oxide gives a mixture of 2 and 3 menthene, whereas the isomeric neomethylamine oxide gives only 2 menthene. Now, what you can see here in these equations clearly is that this NMe2 group, when it is further converted into the N oxide, and when this particular group is getting lost, it can give you these two, whether the double bond is at this substituent, near this substituent which is in 36%, or the double bond is at relatively the far position when you are getting the 64%. So, this is there when in this particular conformation you can notice the IPR and this amine oxide, they are more bulky groups and they are very close positioning and there is steric hindrance. So, there is a predominance of both the possible isomers where the double bond is arising at relative near and far position. So, let us go into the details for these two isomeric molecules when they are going into elimination. Why in this first case the two products are formed, and you can see there is a considerable mixture, 36% and 64%. But on the other hand, when NMe2 and IPR group on this molecule are on cis side, then there is 100% of only one product form. So, let us consider the first molecule. What we see is the N-methyl, N-dimethyl group which has gone into N oxide and the IPR, they are sterically very big, and this IPR and N-methyl, both of them are in equatorial position and they are creating steric hindrance, and that is why you are getting mixture of both the products. On the other hand, if you look at this second case, the N oxide of this N-dimethyl group is now in axial position, and this is relatively far from this isopropyl group. So, what is happening is there is 0% of this elimination which is happening, and there is 100% of this particular elimination which is at the far positioning as compared to this isopropyl group which is there. Now, if we consider the sulfoxides with the beta hydrogen, they readily undergo syn elimination on pyrolysis to form alkenes, and this happens via again its cyclic transition state and in a highly stereoselective manner. The sulfoxide pyrolysis usually plays around at 200 degrees centigrade temperature. The sulfoxide are readily obtained by oxidation of sulfides, which you can do using the metachloroperbenzoic acid or sodium iodate, and the pyrolysis of sulfoxide, it provides a useful route to introduce unsaturation at the alpha position to the carbonyl compounds. So, what you can notice in this particular example is that in this particular carbonyl, when you have alpha positioning this n-ethyl, and you can get the elimination which will be at alpha beta positioning to this carbonyl group. Another example of the synthetic application of sulfoxide pyrolysis is the synthesis of the non-natural amino acid, that is L-vinyl glycine. As you can, let us now understand how the sulfoxide containing substrates will undergo the pyrolytic reaction. Now, when you look at the sulfur and selenium, they both belong to the same group of the periodic table, and they show valencies from 2 to 6. Another thing is that an organic compound is oxidized to sulfoxide and to some extent sulfones also. So, we will get the sulfoxides and sulfones on their oxidation. So, when you have sulfides in the organic compound, that is how the oxidation process is going to. And sulfoxide, they containing beta hydrogen, then these can undergo the beta elimination. And this beta hydrogen, they undergo syn elimination, that is, the group have to be on the same side, and that will be resulting in an alkene. Talking specifically about the diphenyl disulfide, it is used to prepare phenyl alkyl sulfide. From the compounds which contain the activated CH bonds. What are the activated CH bonds? That is, you will have the electron withdrawing group here as well as electron withdrawing group here. So, you can see here in this reaction the oxidation of this sulfide is happening, and as a result we are getting this oxidized product, and it is undergoing this syn elimination. You can notice that this group will be lost and there will be formation of double bond between this carbon and this carbon. And this pyrolytic elimination, notice that, is going via this 5-membered transition state. You can see this transition state is here. So this is a 5-membered transition state. And because of this, you can understand why there is a syn elimination which happens. That is, the orientation of this group or atom and this, it has to be on the same side. Let us also consider the selene oxide pyrolysis. Alkyl phenyl selene oxides undergo pyrolysis to provide or to form an olefin, that is alkene, even at room temperature, and they constitute one of the mildest method for introducing a double bond by means of beta elimination. The selene oxide pyrolysis is also a syn elimination like all the other eliminations that we have studied in this module, and it takes place via a 5-member cyclic transition state. The selene oxides are readily obtained from the corresponding selenites by their oxidation, and they generally undergo elimination under the reaction conditions to give the alkene directly. That is, you can say it is one pot conversion. You need not isolate the in between, you can directly subject to the pyrolytic elimination. So both sulfides and selenites, they stabilize in alpha carbanion, and as mentioned for the sulfoxide case, selene oxide also provide a way for synthesizing unsaturated carbonyl compounds. However, the selene oxide pathway is far more superior due to even more milder conditions employed and direct formation of the unsaturated product without isolation of the selene oxide. So this makes it even better than the corresponding sulfoxides pyrolytic elimination which we had considered. And if you look at these examples, you can clearly see if you have this cyclopentanone, this double bond, you can add this phenyl and SEPH group through these two reagents, and they are, notice the stereochemistry, they are in anti-geometry or the trans geometry, and when this particular can be, selene can be oxidized to selenium oxide, and then this oxide, the selene oxide, on further pyrolysis, that is heating, which is only at 10 degrees centigrade, even below room temperature condition, there will be removal of H and the the selene oxide group from syn side, and that is how you can have the phenyl interact. So you get a double bond where the H and the selene oxide group has been lost, the phenyl is still there. So that is how you can actually do the conversion where you want to replace the hydrogen with the alkyl or aryl group through the dialkyl or the diaryl copper lithiums, as we have seen in this particular case. Let us summarize what we have learnt in this module. We have learnt about the various pyrolytic eliminations and the mechanism, and we have understood that pyrolytic elimination requires the application of heat. The amount of heat may vary, that we have seen some require more heat around 300 to 500 degrees, and some even happen at room temperature. Pyrolytic reactions often occur in the gas phase. Beta pyrolytic eliminations are the most common, although we had also studied the alpha, 1,3 and 1N eliminations are all possible. These are exclusively syn eliminations, and the mechanism involves a cyclic transition state, and it is due to the cyclic transition state that both the groups being eliminated, they have to be on the same side, and that is why there is a syn elimination. We have also studied how some pyrolytic elimination reactions takes place. They also involve the free radicals, and we have discussed the selene oxide pyrolysis, how it provides the milder condition. We have also studied the sulfone oxide, the amine oxide, and out of these the selene oxide, they require most milder conditions for elimination. These pyrolytic eliminations are very important from a synthetic perspective, and these methods have been used for the synthesis of various natural products.